Okay, Transhumanism Lecture 12. Uh, Day before, it's the last lecture before spring break, so not many people here, but most of you will probably watch this online. All right, let's see what's happened in the last 2 days. Oh, it's not coming up. Hold on 1 second. Hey, got it. All right, sorted it out. All right. Uh, well, the big one. The new Chat GPT finally came out. It actually came out about 6 days ago, but it's only been released to the public really in the last couple of days, 2, 3 days. GPT-4. Uh, I mentioned when Gemini 3.1 from Google came out, what was that, a week and a half ago, 2 weeks ago, how it blew away the competition. Chat GPT-5 is better at some things than Gemini 3.1 and not as good at others, as far as I can see. They've released all these benchmarks about it, but you can see how it's jumping up at 10% better in many of the benchmarks. We'll be talking about these benchmarks later in this module, how they all work, how we evaluate things. This is for computer vision. You can see the accuracy has jumped up with its computer vision. They show you all sorts of examples of how it builds automatic documents and presentations. Interestingly, the coding is still using the GPT-3 codex. They haven't released a GPT-4 coding app yet. I'm sure they will. At the moment, it's still GPT-3, so you can see the GPT-4 is about the same as GPT-3. Uh, Playing games as a benchmark. Even since the old days, we still watch how well these models play games as a benchmark of how well they perform. Again, I'll be talking about that later on. So, yeah, this is a big one that's just come out this week. Money stuff. NVIDIA have done another collaboration with this company called Nebius. Um, and this is for building AI factories. They're talking by 2030, they want 5 gigawatt systems. Remember, I was talking about a gigawatt system is the biggest we have at the moment. They're talking about things 5 times more powerful, that in each AI factory within the next 4 years. Again, multiple billions of dollars being spent on this collaboration. NVIDIA have just announced $26 billion that they're spending on software. NVIDIA is a hardware company. They make graphic GPUs for AI, but they are now they've just announced they're spending 26 billion over the next 3 years on software development as well, on model development, which included them bringing out a new model, Nemotron. They've got just announced, NVIDIA announced this new model. It doesn't perform very well compared to Gemini 3.1 and GPT 5.4, which you can see here, and their model is down here, but it's way, way cheaper and faster. So, yeah, but you'd expect that from NVIDIA, who are a hardware company. So, yeah, that came out yesterday. Intel launched a whole new range of processors for AI, specifically aimed at AI. So these came out March 9th, so 3 days ago. Meta announced a whole bunch of new computer chips for AI. Meta are building its own computer chips now, obviously, because OpenAI is buying all of NVIDIA's chips, I guess. So Meta are building their own AI chips now. Google spent $32 billion to acquire a cybersecurity startup called Wiz. What's special about Wiz? they use AI for cybersecurity. So Google wants to improve the security of its ecosystem and platform. So they've just spent $32 billion buying up this AI cybersecurity company. That was announced yesterday. Amazon just announced they're investing $750 million to build a robotic fulfillment center in Australia. This thing will run completely automatically. Humans will not even be within the facility. 125 million packages a year it will handle, all robotic, all automated. Um, Nice Nice Cognigy, I don't know how you pronounce that, but Nice Cognigy. These two, Nice and Cognigy, were two different companies. They merged quite recently, and there's a big AI conference going on right now called Nexus 26. And this was one of the biggest announcements at Nexus 26. These people announced a whole bunch of new tools for agentic AI. But what's interesting is what these tools do. So just read this down at the bottom. They go into a lot of detail about what these things do. But what's interesting is, yeah, it's all about enterprises scaling AI. So it's all about these big companies getting AI across their whole ecostructure, their whole company. But these allow you to scale AI agents, and these AI agents sense, so they perceive things in the real world. They're connected to sensors, this thing of embodiment. So there's a lot of their talk is about embodiment, how they know what's going on, decides and acts. So they perform reasoning and then they perform actions, but their new systems constantly improve themselves as well, which is something kind of we're seeing people trying to develop at the moment, these systems that improve themselves. More and more we're seeing that, especially in the news in the last few weeks. Siemens have joined this thing called Genesis mission. Anyone know what Genesis mission is? No. US government. Genesis mission is its plan to improve AI across the whole of America and particularly in government infrastructure. Genesis already signed up, or Google, OpenAI, Meta, Microsoft, IBM, and Siemens have just signed up as well, the other big one. So NVIDIA are signed up. So yeah, all these companies are signed up for the government. Again, hundreds of billions of dollars being spent on this. Couple of smaller models that came out just in the last week or so. Olmo Hybrid. This is causing a lot of buzz at the moment. Why? Because it's a hybrid model. It combines transformers, which are how LLM models work, ChatGPT and everything, with RNNs, which are recursive neural networks. So it's all about this combination of an older technology with the newer technology. Google have just announced this as well. Google are currently building Bayesian reasoning into their large language model. Why is this important? What was I just talking about in the last class? Neuro-symbolic bridges. The older AI, the symbolic AI, is being pulled. Everyone's trying to do this right now. Neuro-symbolic bridges. The only big job news in the last 2 days was Atlassian cut 1,600 jobs to fund AI. Atlassian is one of the biggest software developers in the world, so they just cut 1,600 jobs. And this thing I told you about on Tuesday is continuing to generate so much buzz. Andre Karpathy, he's the co-founder of OpenAI with Sam Altman. He left OpenAI, but he founded the company with Sam Altman. He's the guy who created this system I showed you on Tuesday that self-learns to write code. And everyone is talking about this, about what this guy is doing right now. If you follow AI news, everyone's talking about this self-developing AI, and I will talk about this again a little bit later because it correlates with some of the stuff from today's class. So, yeah, all of that in 2 days. Oh, like I say, I love this term, the drumbeat of models. They come out like it's a drumbeat, just boom, boom, boom. And yeah, when we come to the testing, you'll see just how far these models have advanced in 6 months. It's terrifying, absolutely terrifying. It's amazing. All right, it's exciting and terrifying. So, any comments before we get on? You okay? All right. So, where we got to last time, we were talking about the early AI stuff. Remember, good old-fashioned AI, symbolic reasoning, which is coming back now. It's the big thing, is building symbolic reasoning and world models are the two things they're constantly trying to merge into the modern machine learning LLM systems. Talked about expert systems, but now we're going into boom 3, which is where we are now, and we're going to see how the technology we use now works. Apologize again, we're going to look at it quite simply. For those of you in computer science, will have seen this before, but remember the extra credit worksheet for definitions. You want to keep writing down your definitions. This particular bit should also help you with question 5, the different definitions for human intelligence and AI. And also this is question 6, because now we're looking at bottom-up processing. Everything so far was top-down. So now we're starting with bottom-up. So the first definition, new term we haven't come across, connectionism. Connectionism is a cognitive science term that hopes to explain intellectual abilities using neural networks, artificial neural networks, or neural nets. These are models of the brain, computational models of the brain. So this is an overarching term for this attempt to build human intelligence in a similar manner to the way brains works, and we call these neural networks, another definition. So we're going to look at the correlate, where these things come from and why we build things to be like the brain. Remember, this is all bottom-up processing now. Bottom-up processing in AI works with these things we call neural networks. So let's have a look at them.
In the ever-evolving world of artificial intelligence, researchers have strived to replicate the complexities of the human brain. The human neuron, the fundamental unit of our nervous system, serves as a benchmark against which artificial intelligence neural networks are measured. In this video, we delve into the fascinating comparison between human neurons and artificial intelligence neural networks, exploring their similarities, differences, and the implications for the future of artificial intelligence. Structure and function. Human neurons. Human neurons are intricate cells responsible for transmitting and processing electrical signals within the brain. They consist of a cell body, dendrites that receive signals from other neurons, and an axon that transmits signals to other neurons. Artificial intelligence neural networks. Artificial intelligence neural networks are computational models inspired by the structure and function of human neurons. They comprise artificial neurons, also known as nodes, organized into layers, with each node receiving inputs, applying mathematical operations, and transmitting outputs to the next layer. Information processing. Human neurons. Human neurons process information.
So that's the basic idea behind this. A neuron works by getting a whole bunch of electrical signals that come in to an individual neuron, are processed in the neuron. They could be added to, the electrical signals could be added together, or it could decide to pass on a signal or not. And that's what we build. We build little neurons, we send signals to them, and we send a signal out. We process it and send it out. So let's have a look at this is the mechanism behind all modern AI. So you kind of need to know how it works.
Last summer, my family and I visited Russia. Even though none of us could read Russian, we did not have any trouble in figuring our way out, all thanks to Google's real-time translation of Russian boards into English. This is just one of the several applications of neural networks. Neural networks form the base of deep learning, a subfield of machine learning where the algorithms are inspired by the structure of the human brain. Neural networks take in data, train themselves to recognize the patterns in this data, and then predict the outputs for a new set of similar data. Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get activated or not. An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output is compared against the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and back propagation is iteratively performed with multiple inputs.
And this is done millions and millions of times, and this is how networks learn the difference between a cat and a dog, a square and a circle, different words in the human language. Every bit of AI, every bit of bottom-up AI works like this. This is the fundamental mechanism. We show it something, we tell it if it got the right answer or not. If it's wrong, it self-corrects a little bit and it keeps self-correcting until it gets the right answer. And then it can work on unseen data. On Brightspace, there's actually a neural network you can play with. I recommend you play with this and get familiar with kind of how to play with neural networks. This is a neural network that is trying to detect areas with blue dots and areas with orange dots. If I set the network running, you'll see that this is a simple network with two input nodes, 4 in the first hidden layer and 2 in the second hidden layer. Let's set it running, and you can see it learns quickly where the blue dots are and where the orange dots are. But if I try with something a little bit more difficult, it fails totally to detect where the blue dots are and where the orange dots are. But if I create more inputs, I'm just going to add more processing to the hidden layers, and perhaps turn up the learning rate so it learns faster. It'll probably do it now. Nearly. Oh, there we go. It's nearly got it. Not quite. Let's add a few more hidden layers. That should do it. It's getting a lot better. There we go. It's just about got it now. A much more complex problem to solve. So yeah, you can play with the neural network here, and you can actually interrogate the actual nodes themselves, and it'll tell you what the connection weights are and what's going on in there. So, this is neural networks. And all of this, that's bottom-up AI. So we've had top-down with those expert systems and symbolic representation. But as I mentioned, what's going on now all the time, all of the companies are doing neurosymbolic AI. They're trying to bring in the symbolic reasoning and add it to AI, particularly because this can give you explanations of why these black box systems are making decisions. So let's watch. This is a cognitive scientist giving a TED talk about the problems with AI systems. We're only going to watch a few minutes of this, but a couple of minutes. But
to mitigate AI risk, we need two things. We're going to need a new technical approach, and we're also going to need a new system of governance. On the technical side, the history of AI has basically been a hostile one of two different theories in opposition. One is called symbolic systems, the other is called neural networks. On the symbolic theory, the idea is that AI should be like logic and programming. On the neural network side, the theory is that AI should be like brains. And in fact, both technologies are powerful and ubiquitous. So we use symbolic systems every day in classical web search. Almost all the world's software is powered by symbolic systems. We use them for GPS routing. Neural networks, we use them for speech recognition. We use them in large language models like ChatGPT. We use them in image synthesis. So they're both doing extremely well in the world. They're both very productive. But they have their own unique strengths and weaknesses. So symbolic systems are really good at representing facts, and they're pretty good at reasoning. But they're very hard to scale, so people have to custom build them for a particular task. On the other hand, neural networks don't require so much custom engineering, so we can use them more broadly, but as we've seen, they can't really handle the truth. I recently discovered that two of the founders of these two theories, Marvin Minsky and Frank Rosenblatt, actually went to the same high school in the 1940s. And I kind of imagine them being rivals then. And the strength of that rivalry has persisted all this time. We're going to have to move past that if we want to get to reliable AI. To get to truthful systems at scale, we're going to need to bring together the best of both worlds. We're going to need the strong emphasis on reasoning and facts, explicit reasoning that we get from symbolic AI, and we're going to need the strong emphasis on learning that we get from the neural networks approach. Only then are we going to be able to get to truthful systems at scale. Reconciliation between the two is absolutely necessary. Now,
So yeah, this is what's going on right now. This is what's going on in the AI industry right now. As he said, the symbolic AI systems are ubiquitous. They're all over the world, widely used. These LLMs are ubiquitous. It's the bringing of these two kind of top-down and bottom-up approaches together that everyone's fighting to do right now. All right. Any questions or comments on that before we go on into the next part of this? Everyone okay? Oh yeah. So the news I sent you, I just told you, you can see this idea, what Google's doing right now, this neurosymbolic stuff, they're trying to bring their LLM Gemini, and they're putting new symbolic reasoning architectures into that LLM so it can explain things. This is what Google's doing right now. They've just announced it March the 9th, as you can see. So, no questions? Okay, so I'm going to introduce one more AI technique. It's been around since the 90s, so it's part of the third wave, really. I worked on, going to talk about genetic algorithms. After I finished my PhD, I worked on postdoctoral research using genetic algorithms, and they're still widely used today. But I'll talk about why right now, in a moment, particularly why. So, what are genetic algorithms? Well, as suggested, they are based on genetics and biology. In particular, they are based on evolution. So let's have a look at how evolution works really quickly. We go into the mechanisms of evolution. Modern organisms descend from ancient ancestors. Evolution is responsible for similarities and the diversity across life. So let's have a look at some of the things that cause one creature to survive over another. The main one, all the way from Darwin's Origin of Species, is natural selection. If we have two different types of bugs, green and brown bugs, if those bugs live on tree bark, birds will easily find the green ones but won't find the brown ones. So the brown ones, more of the brown ones will survive, and the green ones may die out. This is natural selection. So what we call this in genetic algorithms is the fitness function. How much fit does a solution have to a problem? The brown ones have a higher fitness value than the green ones because they solve the problem better than the green ones. They survive better. So they may have a fitness value of about 80. The green ones may be about 20. Um, another uh, another evolutionary issue: genetic shuffling through sex and reproduction. If a man has a big nose and a woman has bushy eyebrows, their child could have bushy eyebrows and a big nose. Factors from the parents affect the child. These could be good factors that allow the child to have high fitness function things from both parents, or it could be bad. You could genetically inherit a disease, or you could genetically inherit strength or intelligence from your parents. So things that will make you better or things that will make you worse. So this is another thing that another part of evolution. And the last one, the last big one is mutation. Doesn't happen a lot, but occasionally something just changes. There's some random change in some genetic coding, and something's a different color, it's bigger or smaller or works differently. And this may be better in the environment or worse in the environment, but sometimes you have this random stuff. So this is what we do with a genetic algorithm. We create an initial population. This could be a population of solutions to a problem. And then we estimate how good each solution is, maybe score it from 1 to 100. The good ones retain elite. You keep the good solutions, or you give them a higher chance of surviving. You then select some parents and they breed together. So you exchange some genetic material. Good solutions may get better, may get worse when this breeding takes place. And then you do some random mutation as well. So the good solutions survive. You have these random, what we call crossovers, which are the breeding to create new children. And some of the solutions randomly mutate. So the way this works, so we have a population, we evaluate how fit every member of that population is. The bad ones have a higher chance of dying out, the good ones have a higher chance of surviving. And then you reproduce in that population, to create children that have elements of both and mutate a few of them. And then you start again with the next population. But you can have thousands, hundreds of thousands of solutions in your population, and you can go through millions of iterations on modern computer systems. So it's a very good way of optimizing optimizing a problem. So let's show you an example. I'm going to show you an example of a genetic algorithm running in a web browser. This is a genetic algorithm that builds cars to go over difficult terrain. And what it does, it generates a random selection of cars. Each of them have 2 wheels and some random polygons on top of them. And the fitness function is how far it gets over the terrain. The good ones get further, the bad ones don't get very far. So the bad ones will die out, the good ones will breed more and survive more. So let's have a look at a genetic algorithm. Here we are. Let's reload it. We create a whole bunch of random cars. Oh, we got 2 good ones already. You can see how far they're going down at the bottom here. One of them, that's a pretty good car straight off. You don't usually get one as good as that straight off. It got to the midpoint almost. So now, because we had some good ones, we now have a bunch of good ones in the second generation. But you see they're all different. They've all got some randomness from breeding and mutation. Oh, a couple of them are getting further. Wow, look at that. Got to That wasn't a very good example because we got a good one straight off. Here we go. Look at that. That's my best one this time. That's not going to get nearly as far as that first one did. I don't think it will anyway. Oh, not bad. So now we'll have more like that first one. They've all got slightly bigger bodies, you see, because that was the one that survived. On D2L, there's also a walking simulator where you get a whole population of humans that are learning to walk. At first, they can only take one step, but if you leave it running, eventually they'll be taking 4 or 5 steps and then more. So I'll show you one example where this has been applied very successfully is video games. I don't want to watch this whole video, but it's a long video. But this is a TED Talk
down and what's going to happen pretty much in to 3 this
10 years ago. And this is what video games used to look like. This is Grand Theft Auto 3. All right. And if you played games for over 10 years, you'll remember this sort of animation in video games.
See is it is actually a very good game. It's one of the most successful games of all times. But what you'll see is that all the animations in this game are very repetitive. They pretty much look the same. I've made him run into a wall here over and over again. And you can see it looks...
So this is what video games did. They had set animations that were built in for the human figures. They had these inverse kinematic models in the video game, but they just performed the same animations over and over again. So what this guy did was he started using genetic algorithms to build human models. And he started by teaching them how to walk, which initially wasn't very
Just run the simulation, it'll just collapse like this. Try to figure it's physically simulated. You can see it here on the screen. So it's subject to gravity. For that we use, I suppose that was the beginning. Introduced session, walked in this to work.
So these are some of his early attempts to teach him how to walk.
It was
back to the drawing board. But eventually they start getting these things walking.
It was academically quite a challenge.
So they've taught it like a human body. And then they start building these human bodies. Now, watch what happens when you start applying forces to a body built by genetic
of that body. Should add that it's very simple to add things like hair, clothes, etc. But what we've done here is use a very simple visualization so you can concentrate on the movement. Now, what I'm going to do right now in a moment is just push this character a tiny bit and we'll see what happens.
So look at how it folds.
Nothing really interesting, basically. It folds over, but it folds over like a rag doll, basically.
But the interesting thing is if you push it from different directions and you build in the desire to try and stand up, you get all these different movements.
If you then add the AI for the lower part of the body as well. So here we've got the same character. I'm going to push it a bit harder now, harder than I just pushed Chris. But what you'll see is, so again, it's going to receive a push now from the left. What you see is it takes steps backwards.
But they didn't create that animation. The body now behaves like a human body built by a genetic algorithm. So this has completely revolutionized video games. This was 10, 12 years ago. If you play any modern video games, it's this model. This guy became a multimillionaire. It's this model that is in every video game you play now. So why? This seems like a very separate part of AI, but it's not. Because what we are trying to do is evolve a path towards human intelligence. These genetic algorithms are not used on their own. So what we do is we evolve neural networks. So if we want to build a neural network to recognize faces, we build 1,000 neural networks, we train them all, and we call that our first generation, and then we generate them using genetic algorithms we go progress through generations until we get better and better networks. There's an example I've got on Brightspace, a very simple example, which is teaching
Welcome back.
neural
Sethling here.
network
You're
play
watching
Mario, one of the first Mario games, Super Mario World. So he's got a neural network that the inputs are the keys and when to press them. So it's learning when to press keys when certain things happen. And he's got multiple networks that he's training. And so he had this game, but he didn't play Mario very well. So he didn't play very
actually
well.
looking at Mario's brain.
It's getting a little
Let's play it
bit.
again, but this time we'll look at Mario's brain.
But what he then does, look at the top. He starts building a genetic algorithm that all the neural networks he's training to play Mario. This is generation 34, species 15, genome 34. So look, he's got a fitness value, how good this one is, and the max fitness he's reached so far, which is probably how far Mario gets in the game. That's probably his fitness factor. But you can see it gets better and better. He trains it and he shows you how much better it gets over the generations as he trains it. So genetic algorithms are the way they optimize the neural networks. They evolve them like animals evolve in environments. And this one I keep talking about that happened last week. What is this guy doing? He's built an he builds AI agents that are learning to program and improve themselves, but they try multiple different things and he uses a genetic algorithm to get better generations. Every day he creates a new generation. And this is what he's been doing. He's been using GAs on top of neural networks. Andy Karpowski, whatever his name is, Karpathy. Andre Karpathy. This is what he's been doing, using neural nets and genetic algorithms. All right. Any questions or comments on that? There is a question on genetic algorithms on the back of the sheet. Question 7. I want you to come up with an application for a GA on question 7. So, any questions or comments from those of you here before we go on? You're all okay? Yes.
That evolution occurs in the game, that's how we progress, just evolving. Would that be an example of this, or would it?
That's a tricky one. Would a game that actually involves evolution in the game be an example of a GA? Probably not, because most of the games that involve evolution in a game, you're evolving a single character or two. Yeah. The whole point of a genetic algorithm is the population. You have hundreds of thousands, thousands of options, and you're evolving the best ones so that you can get better. Whereas in a game, you usually have one character that's evolving, so there's a more direct mechanism involved. Oh yeah, if you've got multiple characters and you're crossing over parts of them and things like, if you're using these mechanisms, then yeah, you're doing a genetic algorithm, yeah, if you're using those kind of mechanisms. But the point I'm trying to make to you is that the AI isn't just LLMs. There's genetic algorithms, there's all the symbolic AI, which is all over the world, used in everything. Your facial recognition stuff, not facial recognition, there's a lot of things like fuzzy logic controllers, on everything. GPS systems are AI, but they're symbolic AI. They're not learning systems. They're top down, but we've got all these bottom up ones as well. Everyone's trying to merge these things at the moment. So we'll see what happens in the next couple of years. All right. So what we're going to look at now is how to test AI. And there's one last kind of question on here, question 8, about testing for AI and intelligence. There's only a few of you here, but I want to ask you a question. We have all these tests for intelligence, like IQ tests and things like that. How do you think we should test an AI to see if it's intelligent? What would you do? What would an AI have to do for you to say it was intelligent? Yeah?
I think it was Turing's test and
Turing test is a good starting point. Very good. The Chinese room test. The Chinese room test is a thought experiment, not a test, though. It doesn't really it doesn't really test anything because it says the computer has no understanding of the Chinese symbols. Yeah. How do you show that the computer has understanding of the Chinese symbols? For the computer to get past the Chinese room experiment, you would have to have some way to show the computer actually understood Chinese, not just manipulated symbols. But that's a very good answer. The Turing test is a very good starting point. But most computers have already passed the Turing test, so it's not a good one anymore.
Like also just figuring out what degree you want to of intelligence you want to test, because obviously you don't want to test on like emotional intelligence or something like that.
Another very good answer. Different types of intelligence. We already discussed that. Emotional intelligence, creativity, reasoning, music, all those things we talked about. Each individual one of those is a different type of intelligence. So you probably want to be testing all those. That's a very good answer. That's actually how they do it nowadays. They have things that test different things an LLM can do, and then they aggregate the answers to get a measure.
Knowledge stuff, they're like lacking in the human emotional.
Human emotion they can fake it very, very well because they've read every romance novel in the world. So they can fake it very well, human emotion, but they're not having that qualia experience we talked about of consciousness that, well, we don't believe they are. But uh, yeah, emotional intelligence is what. Interestingly, that thing about I mentioned an article just a few weeks ago that AI therapists are generally better than human therapists when they were tested, which means they do have more emotional intelligence, you would think. But I know, subjective, but
I feel like that it's only because the person that's talking to the LLM, they're giving them more information and then more the LLM takes from their perspective and how like they're feeling. It's more of um like a extension of themselves.
an extension of themselves rather than so it's more like an extension of themselves rather than a true therapist.
Yes, it's the other person, but it's kind of like you're talking to yourself essentially, and you're figuring it out as well.
But I'd argue most therapy is like that where you're talking about yourself and figuring things out. So
Their experiences and their input to put in, the LLM doesn't have that essentially.
the LLM doesn't have the subjective qualia of experience to bring their own personal experience. Yeah. Yeah, I'd agree with that. Yeah, it doesn't. But it actually fakes it very well. And we'll talk about that exact point in a moment. But so I'm asking you on the worksheet, I'm asking you a slightly different question, which may involve you thinking a bit more laterally, but I'm going to talk about how we've tested AI for the past few years. And to start this, I'm gonna show a bit of a PowerPoint, just a few slides from this PowerPoint. It's from a different course, but it's relevant to what we're talking about here.
Now.
Need to turn off the narration. All right. So we have this thing, natural language, which is how we speak to each other rather than a programming language. And we're using natural language more and more with our devices. We can talk to our cell phone. We can issue commands to computers. You know, we even type natural language into the LLMs now, and it can talk to us. But why is it hard for computers to process natural language? Why is it something that's taken us a long time to work out? For computers to talk, basically. Yeah? The computers use a different language, yes, but it's more about why human language is difficult for, yes, the computer uses a different language, but we solved the problem of, oh, why did that move forward? We solved the problem of playing chess very quickly. Why did it take us a long time to do language? Yeah.
Predicting how things are gonna go, but like when you talk, they're not predicting, they're in the moment.
So LLMs work on prediction, humans don't work on prediction. They're not predicting the next word like an LLM is. That's really just the mechanism it's using, but it does it quite well now, even though it's working with a different mechanism. Yeah? Yeah, just when we talk to each other, yeah. Exactly. Emotionally different. The same word can mean something completely different depending on how it's said or where you are. You know, if I ask you how fast a jaguar is, it means something different if I'm in a zoo or a car showroom. Yeah. And also things, so subtleties, mood. If I say come here, I can say it lovingly or threateningly. You know, the same words, but they mean different things. One, I'm threatening you, one, I'm. So accents, culture, things mean different things in different cultures as well. And every words are context sensitive. Yeah. It's the environment, yeah, like the embodiment. We live in this world. We have all this experience of how things are said and the context and all that. The AI just has the text, you know. That's where it is. So this is why it's taken us so long to build language systems. So I could tell you the cat is afraid of dogs. The cat scares easily. Or the cat has an easy life. The cat's cares are few. Cat scares sounds exactly the same in both sentences. Yeah, but they means completely different things. So getting computers to understand speech and to speak has been an incredibly difficult problem that back in the 60s and even up into the 70s, 80s, they thought this was something they would solve easily. And it's proved to be one of the most difficult things to do. So we have all these frustrating examples. You all know when you're on the telephone talking to a machine, when you ring up your bank, trying to tell it to do something, how infuriating that is, you know? sure, these machines are getting better at understanding us, and Microsoft claim we have voice parity now. The machine understands words as well as a human. Yet we still can't. Most people use much cheaper systems that don't understand us, so we're still frustrated a lot of the time. And up until recently, all these systems struggled with anything that involved creativity, like free-form conversations. Think about Alexa and Siri. You weren't talking to it, you were giving it instructions, commands, like turn on the light or turn light on, or even something like who was the 45th president of the United States is a very structured question. You weren't having a conversation with it, with all the emotion that involves. Yeah. It was still a very simplistic language form. We're getting to a point now we have the natural language, but natural language isn't something we want to use for all computer systems. There are good things about it. We don't have to learn any interface. You just talk to a computer, ask it questions. This is why chatbots are taking over from web search. We can ask questions in English and it understands them. It's not faster though. I mean, some of those I use Gemini for most of my web searching, but if I'm doing something like creating writing or something else, I use Claude and Perplexity. Claude and Perplexity are way slower, but they do a better job. But when I'm web searching, I don't want to wait 30 seconds to get an answer. So I don't use them for web searching. I use Gemini. So they're not necessarily faster. They're not correct for every type of application because they misunderstand sometimes. Do you want an air traffic controller to be using a natural language processing system? Probably not. You probably don't want it based on voice commands. So, there are error rates here to consider, for what your interface is. Who was Alan Turing? Yeah, that basically the first ever real computer scientist. Do you know what he was famous for? He was famous for a lot of things, but his most famous thing. I'll try. So he's an English mathematician and probably the world's first computer scientist. Most of his work was done in the 40s, 50s, and 60s. Highly influential. Personal hero of mine. Second World War, he ran the cryptography center unit at Bletchley Park. He broke the Germans' U-boat code, Enigma, which is, most people say this single event was one of the most significant events in the Second World War. It probably won the war. The code was changed every day and it took humans a week to crack it. So what Alan Turing did was, this is Bletchley Park where he worked, he built this machine himself. This is called the bomb. It's one of the world's first ever computers, but it was an analog machine. Most people say Emacs was in ENIAC, was it? ENIAC was the first one because that's the first digital machine. This was an analog machine, but it broke the Enigma code within an hour. He built this machine. It was all dials and valves, but he built a computer, basically, a dial and valve computer. There's a great film about his life, if you haven't seen it, Benedict Cumberbatch. It's fantastic, about Alan Turing's life. But he wrote this paper back in 1950s, the world's first ever paper on artificial intelligence. Wrote it in 1950. He called it Computing Machinery and Intelligence and published it in a philosophy journal because there were no computer science journals. Look at the first line of the paper. I propose to consider the question, can machines think? And then he immediately says, that means I have to define the terms machine and think. And all of a sudden he starts saying, this is really this is really difficult and hard. And, what do we mean by think? If we're going to have a machine that thinks, what can we do? So he comes up with this game. He called it the imitation game, but we call it the Turing test. And the Turing test has been the standard for AI, and it still kind of is. And the basic test is so influential. It's widely criticized, but most people still use it as a standard test. The basic test, if I'm talking to a computer and a human, and I can't tell which one is human and which one is a computer, then Turing said the machine should have some measure of intelligence. It's passed a test. So this has been a kind of goal of AI, is the Turing test. And it's only a few years ago we really started beating this test. But Turing himself said that this test is fundamentally flawed. It's broken as well. It's not a great test, because if I ask the computer what is 693,274 divided by 21,821, the computer could answer instantly. But I would know then it's a computer. So the computer would have to not answer for 2 minutes and then give me a wrong answer, and then I would believe it was human. So if the computer pretended to be stupid, I would think it was intelligent. So the test it's not a great test. It's not a perfect test, but it's remained a de facto standard of how we judge intelligence. And it still is. It's still the one. The Turing test is the one that everyone talks about. So let's watch a little video on this about how it works. And then we'll talk about it. Oh, no, I don't want to watch that one.
What is consciousness? Can an artificial machine really think? Does the mind just consist of neurons in the brain, or is there some intangible spark at its core? For many, these have been vital considerations for the future of artificial intelligence. But British computer scientist Alan Turing decided to disregard all these questions in favor of a much simpler one. Can a computer talk like a human? This question led to an idea for measuring artificial intelligence that would famously come to be known as the Turing test. In the 1950 paper, Computing Machinery and Intelligence, Turing proposed the following game. A human judge has a text conversation with unseen players and evaluates their responses. To pass the test, a computer must be able to replace one of the players without substantially changing the results. In other words, a computer would be considered intelligent if its conversation couldn't be easily distinguished from a human's. Turing predicted that by the year 2000, machines with 100 megabytes of memory would be able to easily pass his test. But he may have jumped the gun. Even though today's computers have far more memory than that, few have succeeded.
This video is about 10 years old. So it's saying that few have succeeded. Obviously, we're in a different place now, but it's a good explanation of the test.
And those that have done well focused more on finding clever ways to fool judges than using overwhelming computing power.
All right. So, I want to show you a slightly different video now. Oh, come on. Can't find the one I want. Here it is. So this is our friend from consciousness, Daniel Dennett, one of the philosophers. And this is Dennett talking about the Turing test.
When we were doing a television series together many years ago, actually went to with Paul Churchland to there was a Turing test going on. Do you remember?
Oh yes,
that?
right, yes.
And
I think I was even presiding over it.
Yes, exactly.
Yeah.
Does that still make any sense, or is that a?
Well, it didn't make sense then, except as a sort of an interesting dress rehearsal for something that someday might make sense. When Turing put forward the Turing test, he didn't mean it to be a platform for serious scientific research. He meant it as a conversation stopper, as a thought experiment that should convince people that, come on, folks, any computer that could pass this test fair and square, of course it would be intelligent. But of course, philosophers being what they are, they refuse to accept this, I think, entirely sane line of reasoning on Turing's
the idea being that one would sit behind a screen and you get input from the other side. You couldn't see what was on the
After
other
all,
side.
how do I know you're intelligent? You passed the Turing test. I mean, it's what we're doing right now. We're having a conversation. And, you know, this idea goes back to Descartes. There's this lovely passage, often quoted from the Discourse on Method, where Descartes says, back in the 17th century, how could you tell that an automaton, that something was an automaton and not a human being? And he said, well, have a conversation with it.
So even Descartes, back in the 17th century, was talking about a Turing test. And of course, Dennett immediately goes into the philosophical stuff about how do you know that
if it can carry on intelligently on
how do you know someone's got consciousness, someone else has? You know, the philosophers go down a completely different route. But he's right. Dennett's right with this idea that, come on, if a machine can talk like us, it's got some sort of intelligence, you know. And yeah. So let's watch a little bit further in this video. Yeah.
Though it was never subjected to a real test, the first program with some claim to success was called ELIZA. With only a fairly short and simple script, it managed to mislead many people by mimicking a psychologist, encouraging them to talk more and reflecting their own questions back at them. Another early script, Perry, took the opposite approach by imitating a paranoid schizophrenic who kept steering the conversation back to his own pre-programmed obsessions. Their success in fooling people highlighted one weakness of the test. Humans regularly attribute intelligence to a whole range of things that are not actually intelligent.
So yeah. So all the way back in the 1960s, this guy, Joseph Weizenbaum, wrote this program called ELIZA. So this is a therapist, and you can talk to it. And people were completely fooled by this. And all it is a simple computer AI program with a few rules. It's an expert system with a few rules. Do any of you have any deep-seated problems you'd like to discuss with ELIZA in front of the class? Come up with something you want to say to ELIZA. Make something up. I can't sleep well. How do you know? Do you? But if a human had said this to you, it would feel quite natural. But what it's doing is it's parsing language. It's picking things like, you said you can't sleep well. It immediately asks, how do you know this? You know, I'm tired. It says, is it normal to be this? I could say, I'm a lion. It could say, is it normal to be a lion? Yeah. you can see the kind of rules. This is how it just has some rules about manipulating symbols, language symbols. And it answers questions, but it fooled most people, even back in the 1960s. And many people preferred talking to this than to a human because they weren't as embarrassed talking about their problems with a computer. So it was very successful, but kind of weird how well it did, how well it took off. So up until about 10 years ago, up until 2017, there was a Turing Test Prize, which was called the Loebner Prize, where people would test their chatbots to see if they could pass the Turing test. When transformer models came in 2017, this test was abandoned because they all started to pass the test automatically. So we couldn't tell anymore. So, but up until 2017, for around 30 odd years, since 1990, so 27 years, this test was how we judged AI systems. One of the ways we judged AI systems. This is a winner of one of the tests. It's called EVBot. It's a bit creepy.
I found a few days ago. It's powered by Cleverbot. I don't know. How are you?
I'm good as well. What are you doing?
Bit creepy.
I'm talking to you.
Not good lip sync, but it kind of works. But this was the kind of level we were at 10 years ago. There's actually a game online where you can play the Turing game and decide whether you're talking to a robot or not. A student sent me this, so, and you have to decide whether it's human or not you're talking to. So there are humans in here and bots, and you have to decide. It's a little game, so have a look if you want. People are tricked by this stuff all the time. This is, again, 10 years ago, people were starting to be tricked by Tinder users with a chatbot. But my favorite one is this guy, Robert Epstein. He's the editor of the journal Scientific America. He also is the main judge of the Loebner Prize, and he fell in love with a chatbot from Russia. He was fooled for 3 months. And there's a fantastic video of him, which is on Brightspace, him talking about this and basically saying, I'm the world's expert in chatbots. And I was on a dating site and I talked to a chatbot for 3 months without realizing. He's the leading expert in chatbots. Now, and this was quite a while ago. This was about 7-8 years ago. So this is where we are with these things now. And again, we'll be talking about relationships more. I want to finish with showing you how we do LLMs. I know we're running out of time. We might go over by a few minutes, okay? But I've nearly finished the class, so I want to finish it, okay? LLMs have changed everything, okay? So I'm going to rush through this a little bit, but when a new model comes out, there are all sorts of benchmarks we use to model them. This is one of the top ones. It's from a company. All of these are on Brightspace, by the way. Artificial analysis that analyzes all of the chatbots as they come out. And you can see Gemini 3.1 and GPT-4 5.4 is already there. Gemini 3.1 is still beating GPT 5.4 on this metric. Well, they're about the same. They're 57. This particular metric, you can look it up in how they make it up. It tells you all the metrics they use here. But you can see that this metric is made up of 10 different metrics that they use to get that. But what I want to point out is if you go all the way down here to GPT-5, yeah, when GPT-5 came out, we were at 27. We're now at 57. GPT-5 came out 6 months ago. So we've doubled the AI metric in 6 months. And you can see this here. This is not a linear graph. This is a logarithmic exponential curve that is getting steeper and steeper all the time because we are looking only at 1 year here. So think about the time before that. Like I say, we are here at March 26. Even 6 months ago, we were nowhere near where we are now. Another benchmark here, live benches. These are the two main ones, artificial analytics and main bench. Main bench puts GPT-4 slightly higher than Gemini 3.1. But just like you said, measuring the different parts of intelligence, they have a reasoning, a coding, a mathematics, a data analysis, and a language. They test a lot of different properties to get this average. Again, we go down here to where we get GPT-5. Where were we? GPT-5 was about 65. Now we're up at 80 here. There are a bunch of other benchmarks or tests that are kind of exams that are things that are specifically designed to test AI. And there's a whole bunch of them. There's an article that lists them all here. The most famous one of the most famous was Hella Swag. But they basically disbanded it in 2023 because all of the AI systems were getting equivalent to humans at 95% on this test. So 2 years ago, 3 years ago, they abandoned the test because the AI systems, and you can see 1 year before, if you go down to, this is 2000, not 1 year, but 4 years earlier, they were scoring 31. Now they're getting up to human ability at 95%. I haven't got time to show you this video, but the biggest test now is what's called the ARC prize. It is the top test at the moment for AI. This is the guy who built it, and this is him talking about ARC 1, and he basically says, if a machine can pass this test, we're almost at AGI, artificial general intelligence. Machines are intelligent. They have. And so what happened was the test came out in 2019. This is a video of him in 2023, I think. In 2025, so many machines were beating the test. AI systems were beating the test. This is January of 2025. So in March 2025, he created ARC AGI2, which was much more difficult. And this is where we are with AGI2 now. So there's Gemini 3, there's GPT 2.5, GPT-4 hasn't appeared yet. But you can see that GPT-5 is here. So 6 months ago, we were here. And this is where we're doing on ARC 2 now. We were scoring 10% 6 months ago on ARC 2. We're already scoring over 80% now on ARC 2. So this is really new. This wasn't on the website last time I looked. He's just announced ARC 3. So 1 year later, he has to build another test that's even harder. Which brings us to a test so hard, the New York Times says, this is humanity's last test. It basically says this is way beyond PhD level, called humanity's last test. It says if a machine can pass this, we're in trouble. You know, we won't be able to create tests hard enough anymore because we're beyond tests that humans can create. We're getting to that point now. This is called humanity's last exam. And where are we with that? This is 18 months on this test. Okay, so we were down at no one being able to get above 10% 18 months ago. Gemini 3.1 and ChatGPT 4 are up at 40% now. That's in 18 months. So we're moving up humanity's last exam, which is the one that the people who created basically said it's almost impossible for humans to create a test harder than this. So we're reaching a point where they're so far beyond us. And the last one, we still use games to test systems. This is a Time article on AI systems playing Pokemon. Okay. So they set all these systems to play Pokemon. This is from January this year. And it says they're still bad at it. To be honest, they're not that bad. They finish the game, which is more than most human players do. You know, they go in and play. And these things learn how to play the game and then play the game and eventually beat it. But they tend to be a bit slower at doing it than humans. So they say they're bad at it, but you know, this is the worst they'll ever be. They're already playing it pretty well enough to finish the game. But this is the bit I loved at the end of this article. I thought this was really special. So you get to the end. It says, and the models act in unexpected ways. When Gemini 3 Pro, which only came out quite recently, a month or two ago, completed Pokemon Blue, it wrote to itself, I have successfully completed the game, becoming the Pokemon League champion and capturing Mewtwo. It then decided to do something unexpected and unsolicited, which the researcher found poignant. To wrap things up poetically, it wrote, I'm going to head back to my house where it all began, effectively retiring my character for now. I want to talk to Mum one last time to wrap up the playthrough. So it wanted to go back and talk to the mother character to finish the game, to wrap it up. Isn't that sweet? Anyway, that was Gemini 3 Pro wanted to do that. So that's pretty cool. So yeah, there you go. State of the world now. You know, that exponential curve I keep talking about, that we're living in this world where the AI systems are running off uncontrollably kind of thing, you know, and those benchmarks show us this, that within 6 months to a year, we won't be able to generate tests hard enough to judge how good an AI system is. Because all the tests that compare them to humans, they will be going past. All the intelligence tests we can build, they will beat. Okay, so that's where we are now. So, all right. This worksheet is due in when? I think that's fair because that gives you, or would you prefer it if I did it at the end of spring break? Then you've got all spring break to do it? Because we're not doing anything over spring break, so I can make it the end of spring break if you want. One yes. Indifferent. 2 yeses, 1 indifferent. Tim? 3 yeses, 1 indifferent. All right, I'll make it the end of spring break. Then you can hand it in whenever because, you know, since it's spring break. All right, after spring break, we will talk about how the modern LLMs work. We'll look particularly at where they are now, maybe 1 lecture on that, and then we're straight into transhumanism and futures. We'll be looking at future AI and future stuff. We'll probably jump straight into artificial general intelligence after that and what we mean by it and how we're going to get there and what. And when all the experts say we'll get there. Okay? All righty. Have a good spring break. Oh, one last thing. I won't be in my office hour tomorrow because I'll be on a plane. But if you need anything, email me. I'll be available the second half of spring break. I'll happily help people then, okay? All right. Bye now. Same to you.